Okay, we're going to look at the convergence and divergence of some sequences. So I'm going to do some more examples here for you guys. And let's look at this sequence. AN equal to n plus 1 over 3n plus 1. And sometimes in your book, you'll just see it as n plus 1 over 3n plus 1. They're just going to write it in a format that looks like this, where this is your AN. And again, and sometimes it won't have any sort of, I should say indices, but by default, it's 1 to infinity if you don't see anything, okay? So we want to look at convergence or divergence. In other words, we want to say what happens as n gets big. So we're going to say here, as n gets big, a to the n goes to infinity. Right? That's what we want to know. If we have that, we have divergence. If it goes to a finite value L, we have convergence. So we're trying to find what this goes to. We don't know. So let's take a look. We look at the limit. N goes to infinity. N plus 1 over 3n plus 1. And so this question is essentially the same as, if you recall from Calculus 1, they might have asked you, let's change that color, the limit, x goes to infinity, x plus 1 over 3x plus 1. Or even Calculus 2, these are, limits at infinity. And you guys remember that since you have the denominator here, if I can find our highlighter, we always divide by the highest power of the variable in the denominator when we have a rational function. So in this case, we divide really every term by n, but if you really wanted the details, it's, it's multiplying this fraction here by 1. And then you say, okay, am I really multiplying it by 1? Well, 1 can be thought of as, or even replaced with 1 over n divided by 1 over n, which is 1. And that's the same as if you just said to people, because you're going to have to distribute. That's exactly the same as saying things like divide every term by that variable with the highest power in the denominator, because you're distributing. So this is divided by n, divided by n. They're all divided by n. So it's the limit, n goes to infinity, 1 plus 1 over n, 3 plus 1 over n. And at this point, you use properties of limits, meaning the limit of a quotient is quotient of limits. The limit of a sum is the sum of limits. And I guess I'll write every detail here. So we'll say this will be 1 plus that limit, n goes to infinity, 1 over n over 3. I mean, if I do want to write every detail, let me do every detail then. The limit of the constant 1, right? N goes to infinity. And limit of the constant 3, n goes to infinity. Limit, n goes to infinity of 1 over n. So here's what I mean by doing every detail for you. Limit of a constant by these properties is the constant. Okay, limit as n gets big of 1 over n, this goes to 0. And that goes to 0. So we really have 1 plus 0. over that 3 plus 0, which is 1/3. So here's our final answer, 1/3. And so we can say that this sequence converges, right? And it converges to 1/3 here. So just want to remark, this is convergence. Okay. Now I'm going to build on this idea. What if they gave us a sequence that looks like this? Square root n plus 1 over 3n plus 1. And they want us to determine convergence or divergence. Remember, this is your an. So they want to know, as n gets big, where does an go to? In the last example, an goes to 1/3. We have convergence, finite. So in this example, we want to see as well, where does this go to? So I'm going to give you both notation. Limit n goes to infinity, square root of n plus 1 over 3n plus 1. So again, by properties of our limits, we're going to take the square root of that limit, n goes to infinity, n plus 1 over 3n plus 1. And you say, well, we just did that one. That limit goes to 1/3. And you're right. So this becomes the square root of 1 over the square root of 3, 1 over the square root of 3. And of course, we will rationalize the denominator. So you end up here with the square root of 3 over 3. Again, you have convergence here. So here's further examples here of limits with our sequences. And I guess we can put it up here too, since we're square root of 3 over 3. Okay. Interesting. So another example. They might even give you the question, the sequence, this way. So this is another way they describe sequences. And we're going to do the same exact thing. I'm just looking for your book to see if there's anything interesting that we can look at. Okay. So you want to know, as n gets big, where do the terms go to, right? Because this is about n behavior. What happens at the end of this? We're going to take the limit. N goes to infinity. Square root of n over 1 plus square root of n. And like I said, this is completely just like saying the limit as x gets big, the square root of x, 1 plus square root of x. And although technically this is not a rational function in the sense that the numerator and denominator are not strictly polynomials, they're I would say rational like, how you approach this is exactly the same way. Divide every term by the variable with the highest power in the denominator. And that's going to be right here. Square root of n. So you're going to divide like we did before. Square root of n, square root of n, square root of n. So you'll have the limit, n goes to infinity, 1 over 1 over the square root of n plus 1. And again, by properties of limits, I'll do every detail again. The limit of a constant as n gets big. The denominator, we have a sum, so it's the limit as n gets big for 1 over the square root of n plus that limit of 1 as n gets big. Limit of a constant is the constant, so these are 1, and this is actually 0. So what you're really looking at, if we keep that in red, this is 1 over 0 plus 1. So this limit here is 1. Okay. And again, what that means is we have convergence. So we can say here, this goes to 1. All right. Let's compare this question to the next one, that there's a fine detail. You got n, 1 plus the square root of n. Here's my sequence. And like we've been doing, as n gets big, what happens to the terms of this sequence? Limit n goes to infinity, n over 1 plus the square root of n. And like I said, you can think of calculus. Limit as x goes to infinity, x over 1 plus the square root of x. Again, you divide by the highest power of the variable in the denominator. And so in this case, it's the square root of n again. So we divide by square root of n for every term. Okay. Here we go. Limit n goes to infinity, 1 over the square root of n plus 1. And the numerator, by the way, if you note, this is n over n to the 1/2, which is really n to the 1 minus 1/2, which is n to the 1/2. That's going on up here in my numerator. So that's why we have the square root of n in the numerator now. Okay, now if we look at this in terms of our properties, right? Let's see if we did this okay. Yeah. If we look at this in terms of our properties now, numerator, limit n goes to infinity, square root of n over limit 1 over the square root of n plus the limit of 1, n gets big. This value is 1. This value is 0. So I have in my denominator 0 plus 1 here. But the numerator here, this goes to infinity. You see, because this is a strictly increasing function. As n gets big, the square root of n gets big. Okay, it's increasing. So what we have here is that 0 plus 1 is 1. What we say here is infinity divided by 1 here. This is just getting big. See, the denominator is just going to 1. But my numerator is exploding. It's getting bigger, bigger, and bigger without bound. So that's what's going on here. These are limits, ladies and gentlemen. It's not really arithmetic. I'm not doing that. What we're saying is that this denominator goes to 1. Everything here on the bottom is going to 1. That's why we have this portion right here. But the numerator is getting big forever. So this is an example of divergence. This limit is infinity. So as n gets big, an gets big. And these are limits. So the denominator just simply goes to 1. My numerator grows without bound. And that's why we say this whole thing again with our sounds. Let's try to find it.
To infinity and beyond.
And that's what's happening there. Good example. Some pretty good examples. Okay. Let's give you guys another example. And let's do this. Let's put it all the way down here. An is -1 to the n cubed over n cubed plus 2n squared plus 1. A nice sequence. Now, here's what I want you guys to focus on, and I'm going to put this in red here. Okay? What you see here is what I've always described as the alternating mechanism. This is what we've seen in our notes. It's the alternating mechanism. Sorry. Meaning, as we change values of n, because n's going to be, again, 1, 2, 3, and so on, -1 to the first power is what we're thinking of. -1 squared, -1 cubed, I get -1, +1, -1, -1 to the fourth power. That portion, we're alternating between positive and negative. And so the theorem that you guys have here in your book, one of the properties, they say if the limit of the absolute value of an is 0 and gets big, then that means well, this is essentially what it is. It means the limit of an is 0 as well. Your book describes it exactly that way. It's really if an goes to 0 in absolute value, then an goes to 0. And this is as, of course, n gets big. So we have this kind of special convergence to 0. Now, whenever you have an alternating mechanism, this is what you're going to apply, ladies and gentlemen. You're going to apply that absolute value here to your sequence. And this is what this is going to ultimately mean. So let's write this down. It means the absolute value of an is the absolute value of -1 to the n. And that'll be n cubed over n cubed plus n squared minus 1. I'm sorry, I think it's plus 1. So, and now you're going to use essentially properties of absolute value. Now you really only have two properties. You have a quotient rule and a product rule, and that's what we're going to use. So by the quotient rule, meaning the absolute value of a quotient is quotient of absolute values. And then the product rule. We don't have a sum rule, okay? We don't have a difference rule, not in the way you think. So this is what you guys see here. This is the logic that you'll be using. And what I want to remark, if you guys recall, n is 1, 2, 3. N is a natural number. And what that means is the absolute value of n cubed is really just n cubed. In other words, what is under here in your absolute value sign is positive. because the n values are positive. Similarly, let's get our screen back. Similarly, the terms in the denominator are also positive. N cubed, n squared, they're positive because n's positive. So we get to replace that simply with n cubed plus n squared plus 1. So what's going to happen now is we're going to have to really consider the last portion right in here. You might say, what happens to the alternating mechanism? Well, this is what's going to happen to that alternating mechanism, okay? The absolute value, and I'll put that as a note, and you guys want to think of this note. You're going to see this a lot. The absolute value of negative 1 to the n can be described as, this is a product, right? And we know we have n of these multiplied together. So now by the product rule, it's really the absolute value of all these negative 1s. We got n of those too, okay? There's n of these, where each one is the value 1. And you guys know what that really means is 1 times 1 times 1, or 1 to the nth power here, right? Well, that's going to be 1. That's our product. So we get to replace this portion with 1, or in other words, the alternating mechanism is actually gone. So that the absolute value of an is really get rid of that alternating mechanism. And we want to see now, where does this go to as n gets big? So let's put that in red. So where does this limit go to? As n gets big, we want to know where the absolute value of an goes to. Okay, and all that means is apply the limit here. So the limit, n goes to infinity, of the absolute value of an is the limit of n cubed over n cubed plus n squared plus 1. Okay. Now, here's the thing I want you to know. Just like we did in the past, this is strictly a polynomial here in the numerator and denominator. It's a rational function. You always divide by the variable with the highest power in the denominator. And in this case, it's n cubed. So this would be n cubed, n cubed, n cubed, divided by n cubed. So we end up with a limit here, as n goes to infinity, 1 over 1 plus 1 over n plus 1 plus 1 over n cubed. This is what we're doing. And so, by properties of limits now, really, I'm going to go straight to this kind of concept for you guys. I'm not going to write the limit everywhere, because the limit of a constant is the constant. So I'm just going to say to you, I'm using properties of limits here. So you want to make sure you know all those properties. They're the same properties for your limits that you've always had in Calculus 1 and Calculus 2. This limit here is going to 0. 1 over n goes to 0. 1 over n cubed, that goes to 0. So what we have here is really, if we look at the details, and I'll put that in red again, it's 1 over 1 plus 0, which is really 1 over 1, which is 1 here. Now, what this means is the following. Okay, here's the story. As n gets big, the absolute value of n goes to 1. Now, the original question, ladies and gentlemen, was not about finding the absolute value of your sequence. We did it because this is an alternating mechanism. We did it because we were trying to see if we had this special convergence to 0. Now, here's the nice thing about this particular criteria that we just used. That if I go back to the original question, they don't want the absolute value. They want these gone. Okay? They want, the original question was not about the absolute value. This is the original question, right? So here's what is so important for you to know about these examples at this point. Because in absolute value, this went to 1. If we got rid of the alternating mechanism and make those terms positive, well, in absolute value, they go to 1. But because this is alternating in sign, remember that? We got an alternating mechanism. Right here, it alternates between these values. What this is saying is that an goes to plus and minus 1. This is big, ladies and gentlemen. Taking the absolute value like we did when we just look at all the terms as being positive, well, we know this goes to 1. But this wasn't the original question. We proved this goes to 1. What this says is an goes to plus or minus 1 because of the alternating mechanism. And this is not convergence, ladies and gentlemen. This is divergence. Because of the fact that we're looking at how the terms of the sequence behave as it ends. Ultimately, what's the behavior? N gets big. That's what we're looking at. And as n gets big, the absolute value goes to 1, but that means the terms are alternating between positive 1 and negative 1 forever. So, typically I've drawn pictures like this in a graph for students and have said things like this. Here's kind of what this means. Good. Straight line. Positive 1, negative 1. It means eventually your terms are simply going back and forth forever. This could be, it starts anywhere, but we care about how it ends. And we can't define a nice, epsilon neighborhood, like we talked about, around every point eventually, because some of the points are jumping out. They're jumping out of that epsilon neighborhood because you're alternating between plus and minus 1 eventually. So that's what's going on. This could be, for example, I don't know, 1,000. This is 1,000 in 1, 1,000 in 2, 1,000 in 3, 1,000 in 4, 1,005. It's alternating between two numbers. We can't have a epsilon neighborhood that captures every term of the sequence eventually. Well, this is another example of what we say is a divergent sequence. Beautiful, beautiful example. I love this one. So this is pretty deep, ladies and gentlemen, this example. All these examples we're doing are pretty good. So let's take a look at the next one. Cosine 2 over n. This is the sequence. And I'll just go back and say to you, yeah, they can give you this question that looks like this and say, hey, guess what? Tell me about convergence or divergence. They want to know, as n gets big, where does an go to? In other words, take your limit of cosine 2 over n. Now, you guys remember cosine's a nice continuous function. So that means I have the cosine limit n goes to infinity 2 over n. Right? This is just completely analogous to a calculus 1 question. You have cosine 2 over x. You say, oh, that's cosine limit 2 over x as x gets big. And so what you know is that the limit of 2 over n's getting big. This denominator here is getting big as n gets big, and the numerator is a constant. So this portion goes to 0. And so we end up with cosine of 0, which we know is 1. So we have convergence. And very often you can see a question with the answer looking like they say as n gets big, we know that 2 over n goes to 0, which means cosine 2 over n goes to 1. And that's the logic behind working with the sequence in this way for this notation. So this one goes to 1. So I think every one that we have here is a pretty good one. And let's take a look at the next one. Inverse tangent of 2n. Okay, so we want to know, as n gets big, I want to show you something here. Let's do something here. We could transition here. As n gets big, we can say 2n gets big too. Our 2n is getting big. So if I double that, that's also getting big since n is getting big. So the question is going to be, where does inverse tangent of 2n go to? Just kind of showing you the logic and the flow of using this kind of notation. And say, okay, limit n gets big, inverse tangent of 2n, inverse tangent of limit of 2n, right? Yeah. This is what we're looking for. I think here's what you want to think about. Go back, consider the graph. Consider that curve. The inverse tangent curve, if you guys remember, has horizontal asymptotes. And it happens at pi over 2 minus pi over 2. And the curve gets close to this. Gets close to these, horizontal asymptotes. I apologize. Gets close to these horizontal asymptotes. Okay. This is x, this is y. So if you want, we could just simply change this to x and x. So let me do it in purple since that's a little bit of OCD with that, right? We've been writing that portion in purple. We change the variable. So we say the limit x gets big, inverse tangent to x, because ladies and gentlemen, this is a nice continuous curve. Sequences are not continuous. Sequences are discrete. They're just those points. These are curves that are continuous. So what we say as x gets big, 2x gets big, and as these values are getting big, right? These points, the y coordinate gets closer, closer, and closer to the horizontal asymptote that we see here, which is going to be pi over 2. So this limit is pi over 2. And so since these are sequences and discrete, if we look at this as n, these dots, they go to the same location. So this is going to be simply pi over 2. And we have convergence. Okay, pretty nice one. Example. Natural log of n over natural log 2n. Okay, here's another nice example. And again, we want to know, as n gets big, what happens to the terms eventually, right? What happens to an? So you can say, all right, we just take the limit here. And you say, I got the limit, n gets big, natural log n over natural log 2n. And so I want you to remember from calculus, real variable x, natural log x, natural log 2x. A couple of things happened here. Something to observe. That when you take these limits here, right? Because you're going to notice that you get infinity over infinity. The tip-off for me here was the numerator gets big, natural log gets big, and so does natural log double the value. So I got infinity over infinity. And if you said, oh, okay, no big deal, I just use L'Hopital's rule, I'm going to tell you, yeah, you can use L'Hopital's rule, but you can't use it for what's in blue because L'Hopital's rule doesn't apply for discrete points. You need some continuity here for your for your variable x. It's a different course. We call it random variable. So go to the purple version with your real variable x, and now you can apply L'Hopital's rule. And you can say, okay, is that the limit then? As x gets big of 1 over x over 1 over 2x, and don't forget by chain rule, times 2. So by L'Hopital's rule, we have the limit as x gets big, 1 over x over 1 over x, and that's the limit of just the constant 1. A limit of a constant is 1. So this limit here is 1. So what that means here in blue, we can go back now, and we can say, if the domain is natural numbers, it's also 1. And of course, we have convergence. So you do have to go out to the real variable x for a nice continuous function. And this goes to 1. So we can say, I don't know why there's an infinity there. This goes to 1. We have convergence. So this is how you handle some of these questions. Not too bad. Okay. N cosine n pi. Here's another interesting question. So we want to know, as n gets big, where does an go to? Now, I want you guys to notice something interesting. Cosine n pi is an alternating mechanism. Okay? Because what happens here, and we'll put that in red, right? N is 1, n is 2, n is 3. N is these different values. When n is 1, we got cosine pi. When n is 2, we get cosine 2 pi. So let's think. Cosine pi, ladies and gentlemen, is -1. Cosine 2 pi is 1. Cosine 3 pi is -1. Continue. Cosine 4 pi is +1. Cosine 5 pi is -1. So we're alternating here between -1, +1, -1, +1, -1. This is why I say the cosine n pi here is an alternating mechanism. So do what we did earlier. You're going to look at the limit of the absolute value, right? So here, an is n cosine n pi. And you're going to consider only the positive terms and see what happens. Maybe this goes to 0. And if it goes to 0, we have convergence. If it doesn't go to 0, if it goes to any other positive number, well, we have divergence. Let me show you. By the product rule. Absolute value of n, absolute value of cosine n pi. Now remember, this portion here is alternating between positive and -1, plus or minus 1. So the absolute value of plus or minus 1 is 1. And you'll end up now with the absolute value of n, but n are natural numbers. So this is just n. It's positive, right? Natural numbers are positive. What's under the absolute value sign there, or between the absolute value sign, is positive. So that's just n. So what this means is, what we're seeing is that the absolute value of n is n. And so as n gets big, the absolute value of n gets big. It does not go to 0. All right, so this means the positive terms, if we make every term in our sequence positive because we took the absolute value, it gets to infinity. But if we consider what they really gave us, they gave us the sequence n cosine n pi. And so what this really means is that an goes to plus or minus. It alternates in sign, plus or minus infinity. Now, what we say here is that this diverges. So this is divergent because an goes to plus or minus infinity. So the idea is take the positive terms, see where that goes to. If it goes to 0, then you got convergence to 0. If it goes to anything else, it'll be divergent because you're alternating always between plus or minus 1 when you have an alternating mechanism. So that's a pretty big example too. Love that example. I love all of these here. And really on a graph, I mean, if I can sketch this for you guys on a graph, there's this kind of an idea here, I should say, simply of what you can see in some sense is that eventually, right, you got a term here, you keep getting bigger and bigger. I guess that's over here. This is happening. You're alternating forever. So this could be a 500, a 501, a 502, a 503, a 504, A505, A506, A507. They're alternating forever in these opposite directions. They're actually increasing and in some ways decreasing, but that's a whole other story. They're just getting further and further away from each other. They're not ending up in your epsilon neighborhood. They're not ending up in the tunnel, right? So that's what you're seeing here. Okay? The end behavior. And this is another great example. Cosine. Okay, let's try another one here. And then give it to you a little differently. Let's say they have natural log n plus 1 minus natural log of n. And we want to know, as n gets big, oops, not infinity. Where does an go to? I'll put a question mark. I keep doing that. Okay. So we really have to take the limit now as n gets big, and we have natural log n plus 1 minus the natural log of n. And when we do this, we notice we get infinity minus infinity, because the first term here, if n gets big, n plus 1 gets big, which means natural log gets big. And this is n gets big. Well, natural log gets big because natural log is an increasing function. It keeps getting bigger. That's what kind of function it is. And you may see this and say, there's something odd here. It's nothing odd about what I did. Everything here is fine. Infinity minus infinity. But if you're going to try to use L'Hopital's rule, because this is an indeterminate difference, I'll put this as ID. You can't use L'Hopital's rule here because the domain here is natural numbers. You can only use L'Hopital's rule when your domain here is, all real numbers or a subset of the real numbers, meaning you have to have a continuous curve. Natural log x plus 1 minus natural log of x. And you said, okay, you didn't really do anything. And then I'll say, I did something. What I did was, even though this is still an indeterminate difference, I can actually do some algebra here and use L'Hopital's rule eventually. And if you guys remember from your homework, when you have this difference, we have to use algebra, right? That's how we fix this, by using algebra. So in purple, x is a real variable. We have, by the algebra, natural log x plus 1 over x. Okay, because we have what's called the quotient rule. So this is a quotient rule for logs. And then I'm going to say to you, well, what happens? What's the limit here? So if you really focus some more right in here, do some more algebra. This is x over x plus 1 over x, or 1 plus 1 over x. Now, this is going to be good for us. So we have the limit, x goes to infinity, natural log 1 plus 1 over x. Oops, let's do, I guess this is really kind of technically what you see. And so you may say, okay, we're going to try to apply L'Hopital's rule. Well, we don't know. We only could apply L'Hopital's rule to an indeterminate quotient. We just used algebra on an indeterminate difference. And let's see what happens, right? As x gets big, what this means is that 1 plus 1 over x goes to 1. This inside here, for the big value of x, this fraction here goes to 0. So you just have 1, which means the natural log of 1 plus 1 over x goes to the natural log of just 1, and we know the natural log of 1 equals 0. So what we just showed here is that this limit is actually 0. Well, if we change the variable back to n, then what we have really showed is that the limit as n gets big, natural log n plus 1 minus natural log n, we showed this is 0. In other words, this goes to 0, which means we have, again, convergence. It's limit 0. So this is how we handle another nice kind of question here. Okay. Now I'm going to go to this last one here. I'm going to do one more. It's kind of a tricky question. It's interesting, which is why I want to do it. Okay, we want to know, as n gets big, where does the term of this sequence actually go to, right? And so you say, okay, what I'm going to do is I'm going to take that limit again as n gets big, square root of n minus square root of n squared minus n, or minus 1, and you notice we get infinity minus infinity. We get, n is getting big, and n's getting big, right? So that means the square root of n is getting big. And then if we square n, that gets big, and subtract 1, that's still big, and take that square root, well, this is getting big because n's getting larger. An indeterminate difference again, ID. Now I'm going to do this one a little bit different. I'm going to say to you, because if you notice, even though I went to the real variable purple here, I never applied L'Hopital's rule. I thought I was because I have an indeterminate difference. So that's kind of a tip-off. You may have L'Hopital's rule, most of the time, but didn't have that. So I'm going to keep it this way, and I'm going to still use here. Pretend for a sec. We're going to use algebra. We'll pretend it's x, but if I ever have to apply L'Hopital's rule, I have to go back to the variable x, because that's going to make it a nice real variable, and the function's continuous versus this discrete function here. So anyway, here's kind of what's happening here. And then you might say to me, well, what kind of algebra can you use? Yeah, what kind of algebra can we use here? Okay, this is going to be interesting. So for some of you guys, you've never seen this before, and that's okay. I want you to note right in here. Square root of n, I'm going to factor out my n squared, and I got 1 minus 1 over n here for this. So right up in here, all I did was factor out an n squared term. There it is. That's what I mean by factor it out. And you're going to see now something interesting. If I use, let's go out of the highlighter. Square root of n squared, square root of 1 minus 1 over n, where this is just going to be n square root of 1 minus 1 over n. And if I even try to factor again, don't forget, I got that minus, I got this still here. Okay? I got that square root of n. Okay. Now I'm going to say something here about this. I'm going to write this here as, let's see, how can I write this as? I'm going to write it as n over the square root of n. Isn't that the same as square root of n? I think so. It is. So I have n square root of n minus n square root of 1 minus that 1 over n squared. Now, there we go. Here's what I want to say now. Factor out your n. Okay. So I get n 1 over the square root of n minus square root 1 minus 1 over n squared. Let's see what this does for us. Okay, let's see what happens here. Now, we want to take the limit, right? We're looking at as n gets big. So the limit as n gets big of n, 1 over the square root of n minus square root. Yeah, I'm going to do it this way. We're going to see where this limit goes to. Okay, so by properties of limits, let me point out to you the limit of a product is product of limits. So this goes to infinity, n limit, n goes to infinity, 1 over the square root of n minus square root 1 minus 1 over n squared. Now, on this portion here, on the right side, we know this goes to 0. We know this goes to 0, right? 1 over n squared goes to 0 as n gets big. 1 over the square root of n goes to 0 as n gets big. So what you're looking at for this portion here, this is going to be 0 minus square root 1 minus 0 over here. And you say, okay, this is going to be 0 minus the square root of 1. 0 minus, this portion here is simply negative 1. So I go, oh, this limit, negative 1. But what's happening with this? Remember, n gets big. So we end up with n's getting big times a negative 1 there. And a minus times a minus is a plus, meaning this portion goes to negative infinity. Well, this portion goes to negative 1. Together as a product, it goes to infinity. And so what we have shown here, using some algebra again, no L'Hopital's rule, is that an goes to infinity. It gets big. And that's an example here. I think it's minus infinity, sorry. I think I made a mistake. Yeah, this is not negative infinity, it's positive infinity. This other portion goes to negative 1, so that makes this negative infinity, ladies and gentlemen. Sorry about that, because I looked at the question and go, that goes to negative infinity. Yeah, positive infinity here times negative 1 gives you that negative infinity. So this goes to negative infinity, ladies and gentlemen. Let me do that again. But we have divergence. Yeah, you can kind of see it here because, like I said, if n's getting big, notice that's this here is the square root of n. This over here, you're squaring it, so it's getting bigger faster, right? N gets big, n squared gets big. In fact, n squared gets bigger. Even if I subtract 1 from it, it's still getting bigger. And then you're taking the square root of both of those things. This is going to be a negative value as n gets big. So that's why I suspected, wait, something's wrong. It's going to be a negative infinity. And it is. So that's kind of how you're looking at some of these terms here. Okay, at least that's kind of how I look at some. But anyway, here's some additional examples I wanted to show you guys. And hopefully you guys take a look at this over the weekend. And it's good stuff. And so I have done a couple of examples for you guys this weekend. So take care and look it over. We did some great examples here.